Hello everyone and welcome back to Networks class. Last time in class we discussed homework 3.2. So that was the homework in which we made our drug smuggler slightly more realistic. And after that we discussed the projects. So all of you should have now a good idea of what to do in terms of your projects for the next few weeks. And at the end of class we just began discussing max flow interdiction. So we didn't get to finish this topic. But we did go through a few ideas, one of which didn't work and one of which did work. And so the plan for today is to finish that topic, to finish discussing max flow interdiction. And then in discussing this, we'll be able to pull out the general rules of thumb to create an interdiction problem for any sort of network model. And after we're done with that discussion, we'll continue to discuss our last major network model for the semester, which is the minimum cost flow network model. So that's the plan for today. Let's just get into this material by discussing max flow interdiction. So to do this, let's just recall what the max flow problem looked like. So it was maximize over the y and v variables. We want to maximize v. And our constraints looked something like this. So we had trucks going into and out of S, into and out of T, and things coming into and out of every other node. And we had our capacity constraints, and we had non-negativity constraints on the y variables. And to do the interdiction of this problem, we introduced some new variables which had opposite objectives. So here we had a variable for each arc xij that's either 0 or 1 that meant do we attack the arc, in which case it's going to be 1, or don't we, in which case it's going to be 0. And we had some kind of constraints on the x variables as well, so something like maybe the sum of the xij is less than or equal to 5, which says that we can attack at most 5 arcs at once. So last time in class, we discussed the option of maybe writing something like this. So if we add this 1 minus xij, conceptually here, if the x is equal to 1, we're going to cut off the capacity for this arc. So all of a sudden its capacity is going to be 0. But if the x is equal to 0, we just get back the original capacity. So conceptually this made a lot of sense. But it turned out that when we take the dual of the inner problem, we're going to have some pi ij variables here that are the dual variables to this constraint. And they would get multiplied by this right-hand side right here. So we would get a nonlinear objective in the dual. So this didn't work. And so at the end of class last time, we came up with an idea that would work, which was to instead penalize the objective function here. So what we had was we added the sum of dij xij times yij. So here, if the x is 1, for each unit of flow that's going across this arc, we're subtracting a dij penalty out of the original objective function. And we also discussed how if these dij's are equal to something like 1.1, then we're subtracting 1.1 trucks for every truck that's going through the arc, which means that this is a big enough incentive for the operator to just not put any flow on this arc that's been interdicted. So that's the basic idea. And let's just think about what happens if we have this penalty in the objective. So to actually computationally try to solve this interdiction problem, what we would do is we would take the dual of this inner problem right here. And the dual would look something like this. Minimize over x variables, rho variables, and pi variables. The objective would be just sum of uij times pi ij. It comes from these dual variables times these constants, and all the other constants are 0. And then the constraints look very similar to the constraints that we had for minimum cut. So rho s minus rho t equals 1, and rho j minus rho I plus pi ij. And before here, we had bigger than or equal to 0, but now the coefficients of the y variables are dij times xij, and in fact, minus dij times xij. So that's why on the right-hand side here, we're going to write minus dij times xij, because that's the coefficient of the y variable that comes down on the right-hand side. And we have that the pi ij's are bigger than or equal to 0, the rows are free, the xij's are in 0, 1, and we might have a constraint like sum of xij's less than or equal to 5. So we're pretty happy with this result because this is just a regular old mixed integer program that we can solve using branch and bound and stick into any of our solvers. So all of the variables agree on the objective, everything is linear, and so you can stick this into Cplex or GAMS, and you can go off and find interdictions for the maximum flow problem. So let's just kind of pull out what are the basic ideas that make one idea possible and another not possible, or what's the general idea of how to create an interdiction program for a network problem. And the general ideas are this. So to create an interdiction program, we did this. First, we introduced x variables. These are going to be our attack variables that have an opposite objective to the operator variables. And for us, the operator variables were these y variables. So just to see what this means, in max flow interdiction, the y variables had a maximize objective, and our x variables had a minimize. For shortest path interdiction, when we did that, the y variables had a minimize, and our x variables had a maximize. So the x variables just always have an opposite objective to whatever the operator variables are. The second part is that we can introduce arbitrary constraints that involve only the x variables. So these are the kinds of constraints that tell us what kinds of arcs we can attack. So it corresponds to constraints like this, that the x has to be less than or equal to 5. And we've seen in the homework assignment, then this can be much more complicated than this. So for example, in the homework assignment, we had constraints like you can only put a roadblock, one roadblock on an arc going outside of each city. So these constraints here can be very, very complicated, but they have to involve only the x variables. The next thing is that we can have arbitrary constraints involving the y variables. So those are just the operator variables. And so we have some kind of complicated constraints here involving the y variables. We have some capacities, we have these network flow constraints, etc. But probably what's more important than this is how to actually mix the x variables and the y variables. So cannot mix x and y variables in the constraints. So let's see why that is. So we had this idea of mixing in the x variables with the y variables in a constraint right here. But the problem was when we did the dual trick, these x variables became nonlinear, caused us a nonlinearity in the dual, because they ended up getting multiplied by this dual variable in the objective function. And the same would be true if we tried to mix the x variables into these constraints in any other way. So for example, if we stuck some x variables to be a coefficient of some of these y variables right here, when we took the dual, they would end up getting multiplied by the dual variables, and so things wouldn't work out. So the rule of thumb is you're not allowed to mix x and y variables in the constraints. But what can we do? So we can create an incentive for the operator to not use attacked arcs in the objective function. Another way of saying that is that we can mix x and y variables in the objective. So how did that show up in terms of max flow interdiction? Well, right here we're mixing the x and y variables because we have a multiplication of x variables times y variables. But when we do the dual trick, even though it looks like a nonlinearity here, when you do the dual trick, the x's just come down on the right-hand side. They're not multiplied by any dual variables, and everything is nice and linear, and we can solve the dual computationally. And this is exactly the same thing that we did when we did shortest path interdiction. We had an incentive to give the operator against using attacked arcs. In shortest path, that incentive was because we made the arc longer, so it was less attractive for him to use an attacked arc. Here, the reason it's less attractive is because for every truck that the operator puts across this edge, we're kind of penalizing his objective by subtracting some number of trucks from the objective overall. So really, this is the way to cause the operator not to use attacked arcs, is through these incentives in the objective function. And that allows us to basically create something computationally feasible. And the last step here is just take the dual of the inner problem to get a mixed integer program that we can solve. So that's the last step to create an interdiction problem. And you can follow these steps really for any network model. And it applies to more than network models. It also applies to any LP, as long as you can figure out what are the right incentives to kind of put in the objective function to make sure that the operator is not using arcs or areas of the linear program that you've chosen to attack with the x variables. So that's the basic blueprint. And this is going to be very useful to you in terms of doing your projects. So you're going to have to do a step like this to look at attacks on the particular network that you're thinking about. I will put some material online to help you with this. So I'll put some starting points for interdiction programs for shortest path, max flow, min cost flow, and multi-commodity flow. And so you'll likely have to edit these, but at least you'll be able to see some work on some problems that you can use as a starting point. Okay, so let's move on to our second topic for the day, which is the min cost flow problem. So all of you should be somewhat familiar with the min cost flow problem already, because we saw it in an earlier lecture when we were doing just an overview of network problems. So in this problem, we're given some supply demand locations. So we're given some supply demands on each node. And what I mean by this is not that every node has to have a supply and demand. Some nodes might have neither. But we just have some numbers that tell us how much supply is in this node, how much demand is in that node, etc. We're also given upper and lower bounds on the flow on each arc. So an upper bound on the flow is like a capacity for the maximum amount that we could have moving across the arc. A lower bound on the arc tells us the minimum amount of goods that we have to have moving through here. And we're also given costs on transporting a unit of goods across each arc. And our goal is the following. It's to move all the supplies to the demand at minimum cost. So that's the basic description of the problem. So let's just take a look at a quick example to get an intuitive understanding of how this would work. So here's a little network for min-cost flows. So let's suppose that there's a supply of 3 on this node and a demand of 3 on that node. And for each edge, I have a lot of data. I have this cost, a upper bound, a lower bound. So let's signify this like this. So we're going to have 3 numbers. The first number is going to be the cost. The second number is going to be the lower bound. And the third number is going to be the upper bound. So for this edge, we have a cost of 7, a lower bound of 0, and an upper bound of 13. For this edge, we have a cost of 1, a lower bound of 0, upper bound of 1. For this edge, cost of 12, lower bound 0, upper bound 3. And the last one is cost of 5, lower bound 1, upper bound 7. So just by looking at this problem, we can reason out its solution. So this northern route has a total cost of 8, and the southern route has a bigger total cost. And so ideally, we would prefer to ship things on the northern route because it has a smaller cost. However, the northern route has a maximum capacity of 1 that we can ship. So that means we can only ship 1 unit across the northern route, and we have to ship 2 units across the southern route. And we're lucky because these 2 units that we ship on the south also satisfy this lower bound of 1 right here. So the solution here is to send 2 units here and 1 unit across this north route. So that's just one example for picturing min-cost flow. So let's think about writing this into a linear program. And this linear program should look very, very familiar to you. So we're just going to minimize over the y's, and we're going to have a sum over all arcs, the cost of that arc times the number of trucks that we're moving across that arc. And then we have some constraints here. That's the sum of everything going into a node minus the sum of everything going out of a node has to equal some kind of constant BA. And we have some upper bounds on each edge and some lower bound on each edge, and the y's have to be positive. So here are the major differences from things we've seen before. First, we have these lower bounds on the y variables that force us to move at least a certain number of trucks across some of the arcs. And the other change is that with each node, we have this piece of data here that's the BA. So this tells us whether that node has a supply, whether it has a demand, or whether it has neither. And that's what these numbers here mean. So this -3 is the B for this node, and it means that that node has a supply of 3. This +3 is the B for that node, and it means that the node has a demand of 3. And these 2 nodes in the middle, they have neither supply nor demand, so their B is 0, and that's why we haven't written anything there. So those are the only slight differences from previous things that we've seen before. So that's the basic setup of min-cost flow. But let's take a look at a few examples that are really going to give us a little bit more intuition about how this problem works. So here's the first example. We have a network with just 4 nodes. And let's say on this top edge, our data is 103. On this edge right here, the data is 712. On this edge, the data is 607. And on this edge, the data is 723. So if you take a look at this problem for a little bit, you'll notice that the intuitive solution is the following. It's to move 2 across every edge in this graph. So we're going to move 2 along this way. And the reason we have to do this is because of these lower bounds. So this lower bound right here says I have to move 2 across this edge. But if I move 2 across this edge, the network flow or the node balance constraint on this node tells me that whatever comes in has to go out. So that means that those 2 units that came in have to go out here. Same thing here. Whatever comes in has to go out, so those 2 units have to go out here. Luckily, those 2 units already satisfy this lower bound of 1, which forces the 2 units then to go through here because of the node balance constraints on this node. And then everything is balanced here because we have 2 units going out and 2 units coming in. So what's driving the movement here is that the lower bound drives the movement. In this example, if we didn't have lower bounds, we wouldn't have movement. So if you just looked at this problem, you might think that the answer is 0 because we have no supplies and demands. But really, these lower bounds force us to move some material even though we don't have supplies and demands. So here's our next example to consider. So the stop arc has data 103. This arc has data 702. This one has minus 3007. And this arc has data 703. So when you look at this problem, you might think, okay, so I have no supplies and demands, and I also don't have any lower bounds because all the lower bounds are 0. So that must mean I don't need to move anything. But that's not the case because we have this negative 30, and we're trying to find the minimum cost flow. So let's think about what would happen if I shipped a unit around this circle. If I shipped 1 unit, we would make $30 across this arc, lose 7 here, lose 1 here, lose 7 here. But in total, we would have made $15. So the solution here is, again, to just spin 2 units around this circle. Why 2? Well, we're going to spin 2 units because of this upper bound of 2. Really, we'd like to spin more than 2 units because for every unit that we're spinning, we're getting $15 total from spinning it across this cycle. So if I could spin 3 units, I would. But I can't because this upper bound right there is limiting me to spinning 2 at most around the cycle. So in this example, it's the negative cost that we want to take advantage of. That drives movement. And really, we want to take maximum advantage of this negative cost, and the only thing that's stopping us is this upper bound. So let's take a look at a third example. So the example looks like this. So minus 3007 on this arc, 702 on this arc, and no supplies or demands anywhere. So in this problem, we have a cost of minus 30 here, and we'd love to take advantage of it. But if we put a unit of flow across this arc, it means it has to go somewhere, because there's a node balance constraint on this node that says whatever comes in has to exactly equal whatever comes out. So this one unit that would come in would have to come out of here, and this node will also say whatever comes in has to go out. So it comes into this node and there's nowhere for it to go. And so that means we cannot put any units of flow on either of these arcs right here. So the solution here is to just put no flow on any of these edges. And the reason is because we have to satisfy the node balance constraints. So what I mean by the node balance constraints are exactly these constraints right here that tell us how the number of trucks coming into a node have to be related to the number of trucks going out of the node. So in this example that we looked at the beginning, we had this node which said exactly 3 more trucks have to be leaving than entering. This node said exactly 3 more trucks have to be entering than leaving. And these two nodes said that whatever enters has to also leave. So a similar thing is going on here. These two nodes, or these 3 nodes, each are saying whatever amount is entering is exactly the amount that has to leave. Whatever amount is entering is exactly the amount that has to leave. Whatever is entering is exactly the amount that has to leave. And so that's what causes us to have 0 flow on both of these edges. It's because we cannot satisfy these node balance constraints otherwise. Okay, so let's take a look at one final example here. So again, we have 3 nodes. This one has data 7, 1, 2. This one has data 6, 0, 7. So in this problem, this lower bound is telling us that we have to have a flow of 1 across this edge. But that constraint causes a contradiction with the node balance constraints, because there's nowhere for this flow of 1 to come from. And there's nowhere for it to go at the end here. So this problem here is infeasible. If we stuck it into Cplex or GAMS, it would come up with an answer that isn't just 0. It actually says that the linear program is not feasible. So let's just consider these 2 last problems for just one more moment. Suppose that I change these a little bit. Suppose that we put a supply of 1 on this node and a demand of 1 on this node. Now this problem is perfectly feasible, because this node says I can have 1 more truck leaving than entering. So I'd send this truck across. It'll satisfy this lower bound. This node says whatever comes in has to go out. So I have to send that truck across here. And then this node says I can have 1 more truck entering than leaving. And so everything would be satisfied and everything would be perfectly fine. So if I had those supplies and demands, everything would be good. Kind of a similar thing here. If I had a supply of 2 and a demand of 2, then I could send 2 units across, because this supply allows me to be imbalanced here. The demand allows me to be imbalanced here. And I could take some advantage of this negative cost. On the other hand, if this was a supply of 4 and a demand of 4, I would get infeasible. And the reason I would get infeasible is because this upper bound here is 2. So the supply and demand would say that I have to move 4 trucks out of here. If I move 4 out of there, that means I have to move 4 across here. But the upper bound there is 2, so I would get a contradiction right there. So that would cause infeasibility. But the reason that we're looking at these examples is because you can use them to basically just pull out some general rules of thumb about min-cost flow. So these are the rules about min-cost flow, which is basically three things drive a min-cost flow problem. The first are supplies we have to move to demands. So if I have some supply and some demand, I have to move those supplies to those demands. The second is lower bounds we have to satisfy. If there's a lower bound across some arc, we have to put some flow on that lower bound to satisfy. We have to put some flow on that arc to satisfy the lower bound. And the third option of something to drive a min-cost flow problem is a negative cost that we want to take advantage of. So those are really the three things that drive min-cost flow problems, and we saw examples of each of these. So for example, in this example, it was the negative cost that drove the flow. In this example, it was the lower bound that drove the flow. And in this original example that we did, it was the supply and demand here that caused us to have movement across this network. So those are the three options for driving min-cost flow problems. So it turns out that min-cost flow is the most general network model that we'll study. In particular, both shortest path and max flow are special cases of min-cost flow. So let's see how that is. Suppose that you're trying to solve a shortest path problem on a graph like this. So maybe here's S, and here's T, and we have some edges in between with some lengths on them. But the only tool that you have available is a small machine that solves min-cost flow problems. And the question is, how would you solve the shortest path problem using min-cost flow? And the way to do this is pretty straightforward, which is just to give a supply of 1 at S, a demand of 1 at T, and for each of the edges in between, we make the cost equal to the length of the edge. And we're going to give a 0 lower bound. And the upper bound can be anything bigger than 1, because we know we're only going to be moving 1 unit from S to T. So here I could put 1 or I could put infinity, and it doesn't much matter which one because they're both going to act the same as far as the problem is concerned. So this is a way to solve shortest path with min-cost flow. So it shows you that shortest path is a special case of min-cost flow. But perhaps what's slightly more surprising is that max flow is also a special case of min-cost flow. So let's see why that is. So suppose here we have a graph with S and T, and we have some edges in between, and these edges have capacities, and we're trying to find the maximum flow from S to T. But again, the only tool that we have available is a machine that solves min-cost flows. To do this, we have three options to move the flow across the network. So our three options are either supplies that we have to move to the demands, lower bounds, or negative costs. If we have supplies and demands, we have to know ahead of time how much material we have to move. But in the max flow problem, we want the problem to compute how much material is moving from S to T. A similar argument goes for lower bounds, is that ahead of time we have to know how much material we have to move across the arc. But with negative costs, the problem figures out what's the right amount of material to take maximum advantage out of the negative costs. So we're going to use these negative costs to move the flow across this network. And to do this, what we're going to do is introduce this backwards arc with a cost of -1, a lower bound of 0, and an upper bound of infinity. These arcs that are in the graph, they're going to have a cost of 0, a lower bound of 0, and upper bounds equal to whatever their capacities are. So let's think about why this min-cost flow is actually solving a maximum flow problem. Well, we'd like to take advantage of this arc, the negative cost on this arc. So for every unit we put on this arc, we're going to make $1. But to put a unit on this arc, I also have to transport that unit from S to T in the graph. And since I want to make as many dollars as possible, that means I want to transport as many units from S to T in the graph as possible. And the only thing that's going to stop me from transporting more units is the fact that I've reached the maximum flow from S to T in the graph. So this really shows you that max flow is a special case of min-cost flow. So this picture is kind of nice, and it's intuitive about why this minimum cost flow problem is actually trying to maximize the flow from S to T. But besides the picture, you can do this completely algebraically. So let's see why that is. And to do that, let's just write down the linear program for this graph right here. So the linear program is going to have an objective function that's just the costs times the y variables of each of the edges. But the cost of almost everything here is 0, except we have just this -1 cost on the one edge from T to S. So our linear program is going to be minimize over the y's because it's a minimum cost flow. But the only thing in the objective is just going to be the -1 times the flow on the arc from T to S. And then the constraints are going to be the sum of everything going into S. But inside of the sum, one of the variables is this YTS variable. So I'm just going to put it off to the side here. And so that's everything going into S. And then we have to subtract everything that goes out of S. And that's going to be equal to 0 because in this graph, we have no supplies or demands anywhere. So that's why the right-hand side here is 0. So we're going to have a similar equation for T. So everything going into T minus everything going out of T. And one of the things that's going out of T is this YTS variable. So let me just write it on the side of the summation here. And that's going to be equal to 0 again because there's no supplies and demands. And everywhere else we have things coming into a node A, things going out of a node is equal to 0. We have our upper bounds and our non-negativity constraints. So this is the linear program for the minimum cost flow problem described by this graph. So let's just look at this program for a little bit and just manipulate it algebraically. So the first thing that we're going to do algebraically is we're just going to take this YTS and move it on the other side. And what we would get is a minus YTS here when we do this move. Similarly, we're going to take this variable and move it onto the other side. And what we would get is a plus YTS. And the last small algebraic move that we'll do is we'll take this -1 and we'll move it across the optimization operator. So this becomes then a minus, and then the -1 switches the optimization operator, so now it's a maximize. And there we have the YTS variable left inside. So that's what will happen after we move this negative sign. So at this point, it should be quite clear that what's going on is this YTS variable is exactly the V variable that we had in our max flow problem before. So here we had minus V, here we had V, and we were trying to maximize V. So algebraically, this minimum cost flow picture that we created is exactly the same as the maximum flow problem that we've been looking at in the previous lectures. So max flow really is just a special case of min cost flow. So you can think of min cost flow as kind of the most general network problem that we're going to look at in class. So next time in class, we'll take a look at some applications of min cost flow. In particular, we'll look at production planning for a large company. So for example, a car company that might have a number of factories across the world. Each factory could have a different cost with producing different kinds of models. The car company then has to transport those cars produced in its factories to various retail outlets where they have to sell the cars. And so in our application, we're going to try to maximize the profits that this car company is making. So that'll be next time. But this concludes lecture for today. Thanks a lot for listening, and I'll see you all next time.